Hi, in this video we are about to see the packing fraction for body centered cubic crystal structure and its coordination number. Well, here what you see is a model for BCC. In this lattice parameters A, B, C are equal to each other, and the body centered atom is inside. Within this body of the unit cell, an atom is inside, which is in contact with the corner atoms. It touches the corner atoms. So what you see is the corner atom in each face, and the body centered atom is inside. And the lattice parameters A, and B and C are all equal, and the interaxial angles alpha, beta, gamma are also equal to 90 degrees. Now we put this details in a figure. So it is all about body centered cubic crystal structure, BCC. So the unit cell, say in such an axis system, I represent, so this is x-axis, and so this is y, and this is z-axis. And we have said an atom is inside the unit cell. So an atom is inside, and each corner 1/8 of the unit cell. So I put it in this manner. Say one atom, body centered atom, is inside, and the corner atom is touching this body centered atom. These two corners I have marked. Similarly, it is there in all corners. Okay, well then we can go and find the total number of atoms inside a unit cell to find the packing fraction equation. 1/8 of an atom in each corner into 8 corners. Makes one atom, and one atom inside the body center. So totally there are some 2 atoms in BCC. Now coming back to the packing fraction that we have discussed, packing fraction is the volume of the atoms inside the unit cell divided by volume of the unit cell. So here there are some 2 atoms inside. So 2 into 4 by 3 by r cube divided by a cube. Since it's a cube of side A, volume is a cube. Packing fraction equation was small v, volume of the atoms inside the unit cell divided by volume of the entire unit cell. Volume of the unit cell is a cube, and small v is the rest of the things. Okay. Now in this equation we need to substitute for r, atomic radius, so that it may be simplified to get a numerical value to find the packing fraction. Now coming to this figure, I log these corners in this manner. Corner A, and this is corner B, and this is corner C, and this is D. Now in this floor or base, a diagonal AC is to be considered. ABC forms a right angle triangle, so I mark it here. ABC. At B 90 degrees, right angle triangle. Sides AB is A and BC is also A, so this may be written as root 2 into A. So AB square plus BC square and then taking a square root, that happens to be AC. This is the base diagonal. Now I like to find the body diagonal that passes through the body centered atom and reaches the corner atom. A triangle ACD, that is also a right angle triangle. Well, I put it separately here. ACD. Okay, 90 degrees. That AC is the base diagonal, but we have just now calculated. AC is root 2A. AC is root 2 into A. AC is root 2 into A, and this height is CT is small a, lattice constant. So with this, distance AD may be calculated just like our previous step. AD is equal to root 3 into A. There is side AC square plus CD square and finding a square root for that. So there is 3A square, square root is applied, so root 3A is AD. This is body diagonal. Body diagonal root 3A. So root 3A is body diagonal. AD is root 3A. Now in this figure we could see that distance AD is made up of atomic radius here and the diameter and again an atomic radius. So I mark the AD distance here. AD. This is R, 2R, R. So AD distance also may be written as AD is equal to 4R. The same AD distance earlier in our previous step we have marked as is equal to root 3A. So 4R, these two may be equated. 4R is equal to root 3 into A, or R is equal to root 3A divided by 4. So we have made an expression connecting atomic radius and lattice constant, and this is substituted in our packing fraction calculation. Well, here we have said that we are about to make a substitution for R to find the packing fraction. So in this place we are about to substitute the expression we have found now. Say this equation is number 1 and this is 2. So we are substituting equation 2 in 1. EAD we have calculated. That is also shown in this figure also. So we are about to do the substitutions. Packing fraction. Packing fraction substitution. Instead of R, we are about to substitute root 3a by 4. R is to be substituted with root 3 into a by 4. You let it as 2 into 4 into pi, and the denominators it is 3 into a cube. So what I have said now, I have marked it here, and for R, root 3 into a divided by 4. So this is to be cube. This is R, and R cube we need to put, so cube. Well, in this a cube is here. That may be cancelled to simplify. The rest of them are simply numerical numbers, numerical values. So our expected numerical value for packing fraction is calculated using the remaining values. So that comes to 0.68 or 68% is the packing fraction for BCC. Well, now we can go ahead for the coordination number. Coordination number for BCC. In this figure we could see that the body centered atom is in contact with all the corner atoms. In the ceiling there are 4 atoms in the corners that is in contact with the body centered atom. So therefore 4 neighbors in the top section. Similarly in the bottom also some 4 corner atoms which is in contact with this body centered atom. So that makes another 4. So totally 8 is the coordination number. Coordination number for BCC is 8. Let's see that in this model also. Here this body centered atom, green color atom, which is shown as smaller in size, but it's actually touches these 4 atoms in this bottom, also the 4 atoms from the top. So that makes its neighbors as 8. So that was about body centered cubic crystal system. Thanks for watching.